Hello everyone, I am Mohammad Mohsin Rahman Adnan, an EC PhD student at the Ohio State University working under Professor Inam Chaudhary. Today we are going to talk about the ultrashort pulse-induced microexplosion time resolved dynamics in bulk EV silica. So we are actually trying to dynamically measure the microexplosion phenomenon in EV silica and obtain the warm dense material state. So what is warm dense material state? It is the state of matter where it is too hot to be called an ideal Fermi gas, or it is too dense to be treated as a classical plasma. So in figure 1, we can see an elliptical shape of orange color, which we can call the warm dense material state. It usually appears when the coupling parameter gamma and the electron degeneracy theta are both equals to 1. It can be seen in solar cores and brown dwarfs, and also it can be seen in scenarios where internal combustion fusion happens. The goal of our work is to explore the creation of warm dense material using ultra-fast high-intensity laser, and also to characterize the local warm dense material thermodynamics, that is the local thermal equilibrium condition. UVFS warm dense material state had already been achieved in previous works and studied post-processing, but nobody has actually captured the macro explosion dynamics and studied the dynamics with relation to the proposed physics. So we are trying to do that. To do that, we have to create an experimental setup as shown in figure 2. So we have a pump beam with 780 nanometer central wavelength and a pulse duration of 50 femtosecond, focused at a 2.2 micrometer radius with a pulse energy of 3.5 microjoule, so that we get an intensity of 6 into 10 to the power 14 watt per centimeter square. This pump beam is negatively chirped so that there is no or reduced group delay dispersion. We also have a probe beam at around 390 nanometer. The probe beam is actually frequency doubled and frequency shifted so that there is no effect of background self emission to capture the images. We are using a 50 times objective to resolve up to 0.3 micron, and we are using a 16-bit cooled CMOS camera for getting improved SNR. In figure 3, we are showing a flow chart of our calculation. Basically, we are self-consistently solving the Drude model and the US model from Shah equation to obtain a convergence limit of electron density. The final result is the absorbed energy, the electron density, and the warmness material temperature that is later compared with already calculated values. All other parameters are either pre-calculated or are taken from literature. So to find the results, we use shadowgraphy technique, which is an optical method that reveals non-uniformities in transparent media by creating shadows due to reflection of light. So we can see in figure 4 the shadowgraph images, and we can see there are two stages of things happening in the micro explosion. Those stages are explained in table 1. The first stage happens at around 35 to 70 picosecond. We see some ring-like expanding front features arising from the dark center plasma at a speed of 39 to 45 km per second. We call it the shock wave or heat conduction wave. Much later, at around 701 to 702 picoseconds, there are sudden huge changes in the morphology of the dark center and rings at a very high speed. We call it the phase change phenomenon. In table 2, we are showing the calculated parameters from our self-consistent model. We see that the absorbed energy is around megajoule per centimeter cube, and also the electron density is arising from 10 to the power 18 per centimeter cube to breakdown condition of 10 to the power 21 per centimeter cube, and finally settles at 10 to the power 23 per centimeter cube. This final value is similar to the expectations of warm dense material as was shown in figure 1. We also see that micro explosion final temperature is close to 50 electron volt, and the pressure is in terapascal range, which is also consistent with warm dense material state expectations. We calculate the electron ion energy exchange time and the diffusion coefficient, and finally get the heat wave conduction velocity at 38 km per second, which is similar to the velocity we calculated at first stage. So the expanding front features around 35 to 70 picosecond has a velocity comparable to electronic heat wave conduction velocity. In this work, although we have captured micro explosion dynamically and explained parts of it, we are still not clear about the phase change phenomena that happens at around 700 picosecond. So we are trying to explain that phenomena in future works. We thank Professor Dr. Douglas Schumacher for his guidance, and we also acknowledge US Department of Energy for supporting this work. Thank you.